Hi everyone and welcome back to chemistry. This is Mrs. Hutchinson, and as you can see today we're sticking with scientific measurements, but now we're going to talk about accuracy versus precision. So accuracy and precision are often used interchangeably in society, yet they have two different meanings. Accuracy is defined as how close a measured value is to the true value, and here's what we mean by this. So let's just say we have a measurement that has a true value equal to 5.5. Well, let's just say we measured three values, and we measured one at 5.3, another one at 5.6, and another one at 5.4. These are considered to be pretty accurate because they're very close to our true or accepted value. Whereas precision, on the other hand, that talks about how close a series of measurements are to each other. And what we mean by that is keeping with our true value. Let's just say our true value is still 5.5, our accepted value. Well, we could have very precise measurements, but they might not even be close to this value of 5.5. So let's say we've made three measurements, and they came out to be 3.2, 3.0, and 3.1. All of these measurements are said to be very precise because they're very close to one another. However, they're not very accurate because they're nowhere near our accepted value of 5.5. So that's the major difference between accuracy and precision. Now, let's take this even farther. You can have measurements that are both accurate and precise. So let's talk about a knife thrower. I mean, who doesn't like a good knife thrower? So if we take a look here at our drawing, knife thrower deals with, the person that's on the round table and they're spinning, and the person that's sitting right here is entrusting that knife thrower with their life. Well, if we look, the knife thrower doesn't want to kill this guy, so doesn't want to hit him in the head, he wants to hit next to his head. So these, as we can see, these knives are very close to one another, which means that they're actually very, very precise. They're accurate because that's right where the knife thrower wants to hit. He doesn't want to hit the guy in the head or in the body or anywhere else. He wants to make it look dramatic. So that's what makes this measurement both accurate and precise. If we take a look at, say, a dartboard, so another example, taking a look at this here dartboard. And if we change our color to, let's say black. Okay. So what makes it accurate and precise? Well, if we throw three darts and we hit the bullseye is where we want to hit. So since we hit the bullseye, we're saying we're accurate. We're precise because all of the measurements that we have are close to one another. So that's why this particular situation is both precise and accurate. Now, we can have measurements that are neither accurate nor precise. So again, back to the knife thrower. This is a sad, sad day for the poor man who risked his life. We can take a look and we can see, well, they're not precise because all of the knives are not even close to one another. They're not in a cluster. Therefore, since they're not clustered together, they're not precise. That's the first part. The second part, well, they're not exactly where the knife thrower wanted them to be. He wanted them to be over here, next to the guy's head. He didn't want to kill him. Unfortunately, he injured his foot, his thigh, and, well, I think the one in the chest might bode very badly for this guy. So since the knives aren't where he wanted them to be, these measurements, or knife throws, are very inaccurate. So this is an example of measurements that are neither precise nor accurate. And we can take this example and we can apply it to our dartboard. So remember, in order for us to be accurate, we want to hit the bullseye, and in order for us to be precise, we want our measurements to be close together. Well, what if we threw one dart, whoopsies, what if we threw one dart over here, and one dart over here, and then one way over here, because this is what happens when I play darts. So, these are not very accurate. They're nowhere near the bullseye. They're nowhere near where I actually wanted to hit. And they're not precise because they're not close together. So this is a prime example of when we're neither precise nor accurate. Now, we can, however, have precision without accuracy. What that means is that our measurements can be closely grouped together, but it might not be exactly where we want them at all. So if we take our little knife thrower example, yeah, they're pretty well clustered, so that makes them precise, but we killed the guy. We didn't hit next to his head where we wanted to. So since we didn't hit where we wanted to, we're not accurate. One would hope he didn't want to hit this poor man here. Otherwise, he's going to be on trial for a long time. So going to our bullseye example, we can have measurements that are precise and not accurate. So let's say we had one dart here, and, well, another one right there. They're very close together, so they're precise, but they're nowhere near where we were trying to actually aim, which is our bullseye. So they're not accurate. Now, question is, can you have accuracy without precision? So really think about it. Think about the definitions of accuracy and precision. Accuracy means that they're close to the measured value. Precision means that, well, they're close to one another. So if the values are close to one another and they're close to the accepted value, then wouldn't you say that they're being both precise and accurate? So think about this. Accuracy means you have to have them close to the measured value. So here's our little bullseye. Accuracy means you want them where where you're aiming. These darts would be accurate. They also have precision because they're all close to one another. They're all close to our accepted value. So some people may argue that you can have accuracy without precision, but I don't believe you can. So now let's figure out, how can we tell if the data that we're dealing with happens to be accurate? Well, again, accuracy is close to the true or accepted value. And in order to determine if the data are accurate, we have to first know the actual value of the thing that's being measured. Now, the accuracy of a measurement is expressed by a measurement's percent error. And this is found on reference table T. Reference table T is the last reference table on your chemistry reference tables. So if you flip all the way to the back of your reference tables, you'll find this one. And you'll find that percent error is the third one down. And it says percent error is equal to the measured value, so what you actually measure, your experimental value, minus the accepted value, meaning what's actually given, what you're hoping to get, over the accepted value, times 100. We multiply it by 100 because If you break this word down, percent means per 100. So that's why we multiply it by 100. So here is my interpretation of reference table T's equation. This one's my interpretation. You can write down either what I wrote here or what I wrote here in your notes. Either one. So I like to say it's experimental value minus accepted value over accepted value. But it's either way, measured or experimental, happens to be the same. If you have a high percent error, then the data that you're dealing with, it's not very accurate. You want a low percent error. You want to keep it, I tend to tell my students, below 10% error. That means that you're doing a really good job. Now, is that likely to happen? Not in a high school chem lab, but it can happen outside of high school chem. So here's our example. And let's change our colors. Black is boring. Purple. So the mass of a sample of a compound was found to be 45 grams. If the actual mass of the compound was 55 grams, what is the percent error of this calculation? So the mass that we found was 45 grams. So that means that our experimental value is equal to 45 grams. Because that's what was actually found. The actual mass, or our accepted value, in this question, is 55. So using reference table T, and using our knowledge of chemistry, it's experimental value minus accepted over accepted. So we've got 45 grams minus 55 grams over 55 grams times 100. Now, how we solve for this, hopefully we know a little bit of math. You take your 45 minus 55, you'll get your minus 10 over 55 times 100, and you'll get negative 18.2%. Okay, whoa, can't see it, so I will write it up here, 18.2%. Now, why is it negative? It's negative because if we take a look, our experimental value happens to be less than our accepted value. That's why. You can, if you want to, take the absolute value of percent error. So that is something, if you want to do it, you can absolutely do that. Next example, we have a student calculated the area of a piece of zinc to be 3.7 centimeters squared. The real area of zinc was 4.0 centimeters squared. What was his percent error? So if we take a look, we've got 3.7. That is our experimental value. We then find that 4.0 is our accepted value. And you will find that my handwriting really is as bad as it looks here. So we do 3.7 minus 4.0 over 4.0 times 100. So you'll get negative 0.3 over 4 times 100. And that's equal to negative 7.5%. So again, I'll rewrite it up here for you. And again, it's negative because our experimental value happens to be less than our accepted value. So now what I want you to do is work on our accuracy worksheet. I'm going to help you start this particular question, but I'm not going to help you finish it because I think you should practice that. So it says a student finds the density of a liquid to be 0.1369 grams per centimeter cubed. The known density of that liquid is 0.1478 grams per centimeter cubed. What's the student's percent error? So again, the hardest part, in my opinion, seems to be probably pulling the information from the questions themselves. So we've got our experimental value. And in this case, when it says a student finds, that means we're talking about, well, what did they find in the experiment? So our experimental value is 0.1369 grams per centimeter cubed. And our accepted value is 0.1478 grams per centimeter cubed. And from there, you can use reference table T to help you plug in all of this information. Okay? So enjoy doing that worksheet. I hope you had fun, and I will see you next time.